So as for what concerns the references about the things that I've done so far, so for measure theory, well, any good book on measure theory covers the disintegration theorem and the Kolmogorov theorem that I'm going to discuss today. I think a quick, a good introduction, you can find it on Dudley's book, Real Analysis and Probability. Sometimes the presentation is a bit more probabilistic in some sense oriented, but even if you don't know probability, that's okay, or should be okay. And for optimal transport, well, there are several. Again, I mean, now optimal transport is quite a well-known topic, and there are several references to it. For what I mean, we really need just the basics of optimal transport, so nothing too complicated. And for that, an introduction to optimal transport theory and application that I wrote a while back is more than sufficient. Just the first chapter and half of the second is more than enough. There's another version of this book that I wrote with Ambrosio. It's called The User's Guide to Optimal Transport, and it's basically the same content. But of course, besides that is sometimes as far as I know, the quickest way, of getting into the things that we need. But there are many other introductions to optimal transport, and not only introduction. There's the book by Villani, Optimal Transport Old and New. There is a recent survey by Figalli and Glauco. I don't remember the title, but I think if you look Figalli, Glauco, and on archive, you will find it. There's a book by Sant'Ambrogio, Optimal Transport for the Applied Mathematicians, that also covers at least some, the generality of what we will need, although we will go quickly to metric spaces and so on and so forth. That is not very much covered by the book, but still, the basic ingredients of the theory are there. And then there is the book by Ambrosio Savarin and myself about gradient flows, I guess, on metric spaces, and in the space of probability measures, that also covers most of what I've done and will do in optimal transport. Okay. With that said, yeah, we can start. So I had to conclude the proof of this integration theorem. So let's go. Oh, questions? Okay. So we start from where I interrupted last time. So we had, let me recall just the the setting. There was a map, Borel phi from polyspace X to polyspace Y. There was here a measure mu. Here we have the measure nu, which is phi push over mu. And we were disintegrating mu according to this map phi. So we were looking for a family of a Borel map from Y to the probability measures on X, weakly Borel. And such that mu of E was equal to the integral of mu Y of E in B mu Y for every E, Borel in X. And these guys, this mu I should be concentrated, concentrated on the pre-image of Y. Maybe it was T the other time, but I don't remember. So it's other phi, okay? For mu almost every Y, okay? And we actually built a family of maps, a family of measures, weakly Borel, and the definition basically ensures that mu Y of E was equal to the density, the Radon-Nikodym density of phi push forward chi E mu d, okay, phi push forward mu, if you want, this is mu, at the point Y, for mu almost every Y. Okay, so that we gave it, we have been able to prove that there is such a family of maps, of measures, and I still need to prove this family of measures, sort of by definition, they do satisfy this identity, and I needed to prove that it is concentrated on the pre-image of phi. That's what it remained to be proven, and this comes from the following identity. So I guess the claim is, let me see. Yeah, the claim is that for every E, let's say Borel in X, and say A Borel in Y, we have the identity that the mu, so the integral over a of mu y of e in the mu of y, this is equal to mu of e intersection pi minus 1 of a. Okay, so I claim that this identity holds. All right, and why is this the case? Well, let's just work with the definition. So this, I mean, if you believe in the formula that we proved last time, this is equal to the integral. Let me write this way of I guess chi. Let me write like this: d yes, d phi push forward e mu d nu, right? So again, I will sort of simplify, and this is equal to the integral. Well, this is equal basically to phi push forward chi e nu of the set A, right? And this is equal to this, right? By sort of basic definition. All right. Now, if you have these, what it is that we can conclude? Now pick. Now let A vary on a countable set on a countable collection of Borel sets, such that such that for every what is that I want that this for every point in the target space, I can find a sequence of set whose intersection is exactly equal to that point, a decreasing sequence of set. So for instance, pick as A the collection of balls centered in a dense setting Y with rational radii. Okay. Now, and we apply that formula for E equal to phi to the image of A. So we get that the integral, let me write it this way. So mu y of preimage of A d nu of y, this is equal to mu, well, this is equal to nu of A. Right? But because there is no intersection of E, so that's E is equal to 5 minus 1. All right. Well, but given that, now look at this. So given that all these are probability measures, right? So this integral is by mass consideration, this is less or equal than this right hand side. So the fact that there is equality ensures that for almost every y in A, this guy has to be 1. Right? And now basically we are done. Right? Because now what do? You pick y. No, now you let A vary in this countable set. No? And then you deduce that for nu almost every y, we have that if y belongs to A to an for some n, then mu y of phi minus y of an is equal to 1. Right? And then we are done. Pick any such y. This measure is concentrated on preimage of an for any n for which y belongs. You intersect all of this, and mu is concentrated. All right. Okay. So it remains uniqueness. The uniqueness statement, remember, was like this. I should have, suppose that I have another weakly Borel map for which this and these are true. Then, let's say mu tilde, I don't know, say mu y tilde has the same properties. Then, not same properties. Then the uniqueness is that mu y should be equal to mu tilde y for nu almost every y. That's the uniqueness statement, right? Which is the strongest kind of uniqueness statement that you can hope for out of an integral identity like this. You can always change these measures on a negligible set, and this is not right. And why is that the case? Well, let me claim that. Let me claim that this is also true for mu tilde. We already know that for our mu, that statement is true. Let me prove that this is true for mu tilde. And why it is so? Well, I make a slightly different computation. And the computation is that, so let me see. Oh yes, so again, I write this as the integral. Well, let me perhaps I guess that the claim is this. So if mu tilde y of e characteristic function of y, this is equal to mu tilde I of e intersection pi minus 0, right? You know. So the point is this: if mu tilde y is concentrated on the preimage of y, then this formula holds. Okay. Why is this the case? So let's have a look to what is written on this formula. So on the left hand side, I have the measure of some set multiplied by this characteristic function. Now this characteristic function is either 0 or 1, according to whether 1 if y belongs to this set, 0 otherwise. Okay, if y belongs to this set, this basically is not here. But if y belongs to this set, I mean, mu is concentrated on this set. So taking this intersection makes no difference in computing measures. Okay. So if y belongs to A, and this holds, this is true. But if y is not on A, then this left-hand side is 0. Right? But also the right-hand side is 0 because mu and y is concentrated on this set. And therefore, when we take the intersection, okay. Now you integrate and you get this, right? Therefore, you see what we can conclude is that the integral over a of mu y e d mu y is equal to the integral over a of mu tilde y e d mu of y, right? Because both are equal to this expression where mu tilde and mu y do not appear. But now again, and this is true for any couple of Borel sets on the source and on the target space, right? But then again, we know that there is a countable collection. So we have probability measures on a separable space, and then we know that once we look at the value of these probability measures on a certain algebra countable that generates the Borel sigma algebra, if they agree on that algebra, they must agree everywhere, right? So I play with this fact in here to deduce that first of all, so I let A vary on this countable algebra to deduce that mu y. So for any Borel set E on the source space, I know that this is true for mu almost every y. You agree? Actually, if you want, this requires even less. No, so fix E. Look at the function of y that gives you mu y of E and mu tilde y of E. These two functions integrate to the same real number whenever I integrate on any Borel set A. So they must agree almost everywhere. Okay. Now let me play with the fact. Now let E vary on a countable set generating the sigma algebra and the source space. Okay, and so you know that this is true for mu and for every n. Right? But once you know that two probability measures agree on a certain well-chosen countable set of countable collection of set, then they must agree. Okay, end of the. Right. All right. Let me remind you. So on what? So as for what concerns the existence of this probability measure, I relied on the following basic lemma of measure theory. Let me insist on this fact because I'm going to use once again it now. That does the following. Suppose you suppose A is an algebra of set, say of subsets of some space X, just a set. I mean, this is no additional. And mu from A to, let's say, 0, 1, just for simplicity, is finitely additive. It's a finitely additive measure. Finitely additive measure. Then you can wonder under which conditions this extends to an actual measure on the sigma algebra generated by A, well, then mu extends to a measure, count of a measure, no? On the sigma algebra. Generated by A, if and only if mu of Cn goes to 0 for every choice of sets Cn inside A, Cn included, I mean, the sort of decreasing choice of sets, and such that the intersection in N of all the Cn is empty. So I'm asking for continuity from above. Okay. In general, you will not see this from continuity from below without the requirement that the measure is finite. I mean, for simplicity, I'm putting one. Okay. Now the proof of this result is totally trivial. Okay. It basically, you start from such a finite relative measure, you build the outer measure generated by by this measure. So you try to cover any arbitrary set with sets, with a countable collection of sets in the sigma algebra, and then you do the inf or all the possible coverings of the given of the sum of the measures. And basically, this condition is what ensures you that the sets in the algebra are actually measurable, and that the measure of these sets coincide with it. Okay, it's an exercise in measure. Okay, I'm pointing this out because there is another quite simple, I mean, there is a rather direct consequence of that result, which also has, for some reason, a bad reputation among students, and I want to sometimes convince you that there's no need to be scared of this result. And it's Kolmogorov result about existence of measures with given what is sometimes in probability terms is called conditioning in a finite number of events, but for us it's just existence of product measures. So theory, Kolmogorov, and I will stick to the case of countable products. The theorem is valid in much more generality. So let Xn be Polish spaces. And let me call Xi. And for every n, let's say let's call it, I don't know, alpha n be a probability measure, not on the Xn, but on the product from I equal whatever, 1, 0, whatever, to n of these sets Xi. Okay, so for any finite number of these, you have a probability measure on the product, and then let's assume that for every say n smaller than m, if I take the projection from, I don't know, from m, then I do this push forward alpha m, I get alpha n. Okay, so what is this map? This map is the map projection from m product to n product. So, no? X1. If m is bigger than n, no, this product is bigger, and you have a natural projection. Okay. Then there exists a unique probability measure alpha on the infinite product of this Xi, such that the projection from, let's say, infinity to n of this alpha is equal to alpha n for everything. Okay. So what does the theorem say? So the theorem wonders about the existence of a certain probability measure on an infinite product. Okay. And you observe that for given finitely dimensional marginals. Now notice that if you have a probability measure alpha and probability measures alpha n satisfying this constraint, this must be true, right? By some sense post-composing projections. So this sort of compatibility must be there. Okay. Kolmogorov theorem tells you that as soon as you have that compatibility, you also have existence and uniqueness of the given measure. Okay. Proof. Proof.
It seems like the obvious case would be if you have one measure on every xn and then on every xi and then outside the product.
Yes, sure, sure. That's in particular a possibility. Sure. Of course. Actually, yes, and you will see many of those in optimal transport. So let me well, okay, let me give you another trivial example, sort of in the opposite direction. Imagine that all the xi's are the same, and imagine that all of these alpha n are concentrated on the diagonal. So for instance, no, you fix a probability measure mu on 1 and therefore on all of those, and then you can consider the map that sends x to x comma x in Tn. And then you can do the push forward of this measure under this map, and this gives you a measure concentrated on the diagonal. That's the opposite direction. This is extremely concentrated. You made it up extremely diffuse. This is extremely concentrated. And of course, in this case, what is the resulting measure? Well, of course, is the one that sends. Of course, right? Can be anything, right? Let me comment. Perhaps another comment I should make. A countable product of Polish spaces is still Polish, right? Why? Because you can endorse. So what does it mean? Being Polish means that the topology, which in this case, of course, is the product topology, is induced by a complete and separable distance. And then the distance, the distance that we put on over here, the distance between two sequences, xi and say yi. This is, for instance, one distance, and this is something like what is 1 over 1 plus 2 to the power I. The distance between xi and yi mean 1, something like this. No? And that's one example in which you see that the actual distance, is totally irrelevant. I care about the topology. You can put whatever you want. Okay. Okay. All right. Yeah, good. Thanks for asking for examples. Please do that. Sometimes I might sort of forget. Proof. Okay, there's one clear set collection of sets for which we know what this measure alpha should be. Okay, and these are the cylindrical sets. So let A, subset of, I don't know, collection of subset of X. In Italian is a set of parti. I don't know in English what is set of subset 2 to the, what should I write? 2 to the, what should I use? 2 to the X? What should I write? I don't remember the denotation. A collection of subsets, and so this is the set made of those guys of the form of those are A subset. Let me write X infinity just to denote the product space, such that A is equal to pi infinity n minus 1 for some an for some n in n and an Borel in xn. These are called the cylinders. Right? Yeah, for I guess more or less obvious reason. Okay. Now these clearly form an algebra exercise. No? The complement is there, finite as far as you only take finite, number of operations, you do not exit the range of cylinders. Of course, if you take countable, countable intersection, then you might be, in trouble. You can be not anymore a cylinder, but that's not. So this is an algebra. Okay, and it's clear that if I define for such an alpha, for such A, if I define alpha of A to be equal alpha n of an, okay, that's what I want to do. Okay, and the assumption, this assumption star ensures that this is well posed. It's an exercise. I mean, there's nothing hard. This is what do I mean by this is well posed? Well, maybe the same set A can be written in different ways in this form. Right? For instance, I could add to A, I could take AN, multiply by the whole space xn plus 1, and that's another base of a cylinder. Okay. But because of that, doesn't matter which one. Okay. So this map is well defined. Okay, and it's easy to check that it's finitely additive because for trivial reasons, because these are finitely additive. Okay, so all I need to prove is that this is true. If I prove that this is true, it's clear. Then okay, extends here. The extension is unique. Okay, for trivial reasons, the extension is unique because once you have the okay. No, because any set can be in the sigma algebra. You can approximate by these kind of guys. Okay. So it's the hard part here is the existence of these measures, not the units. Okay. Okay. Well, suppose not. Okay. Suppose that it fails. By contradiction. Say that say that the alpha of Cn remains bounded from below by some delta. Cn's are like this. This, of course. And let's see what we can do. And actually, I will do something. Topology has to come into play as usual when some limit occurs. And again, I will use once again the tightness of probability measures on polyspaces to help me conclude. So, because what do I do? Actually, I can also assume. I mean, to force it, I will explain in a second why I can do this. So that Cn is of the form Cn. Sorry, pi. What is it? The pi infinity n minus 1 of some Cn prime. For Cn prime Borel in the product of the first. Just so I have this a priori this decreasing sequence, and let me assume that it is of this form. I can always reduce to this case because so C1 is a D preimage is some cylinder over the first product of few guys. Let me call the product of the first these few guys x1 prime. And then C2 is another cylinder, so up to adding some other factor, let me call this other factor x2 prime and whatever, so I can always, for simplicity, reduce to this case. Okay, just to don't get crazy with indexes. Okay, okay. So let me say that this is the case, and then you give me epsilon, and I find a compact set K1 inside this Cn prime, such that C1 prime, inside the first, such that the measure of the difference, so mu1 of C1 prime minus K1 is less than epsilon. I know that every single probability measure, sorry, alpha 1. Any probability measure on a Borel any Borel probability measure on a polyspace is tight, and therefore I can do this. Okay. And now let me consider the sets. Okay, let me consider these sets. C and I don't know, bar. This is the this is Cn minus intersected the pre-image, how to say, n1 minus 1 of k1. Okay, so what's the picture here? I have okay, I have a lot of products, so it might be the hardest. So I have a first cylinder, which is like a cylinder over a set C1, and then I have another set which is a cylinder over, you know, it's like of this form, it's like the product of two guys. And what I'm doing over here, I'm first of all, I'm sort of almost filling this base cylinder by the first compact set K1. Okay, this is C1 prime, this is K1. And then what do I do? I look at the cylinder built over K1, and I, you know, restrict the other cylinder by intersecting it with the dimensions. Okay. What is clear is that these guys now are still decreasing, and still the intersection is going to 0, to the empty set, because these are smaller than C. And once I, you know, I have a decreasing sequence of set, I make the intersection with, okay, morally the same cylinder. You see? Make sense? Maybe I'm a bit confusing, some confusing definition. Oh, perhaps what should I? Perhaps let me. Okay, with the same cylinder. Okay. Make sense? Please.
What's the superscript on the protection?
With this one?
Yeah.
One. I mean,
oh, just one.
Just one. So this is a, you know, a first compact set on the first guy. So I'm just taking, you know, this is the projection from the whole product space to the first coordinate. And I'm taking the cylinder with base K1. Then take this cylinder and I intersect with all of this. Okay. So now these new guys are still go to 0 and just a little bit smaller, right? And I should also notice that sort of how could I put this? So alpha n of Cn prime intersected, you know, well, basically, okay, I'll tell you informally what I mean, and then I'll prove it. So in principle, you know, the measure alpha of these guys in principle should always be bounded from below by delta. Okay, I don't have a measure alpha, so that's why I'm not writing, but that's what I have in mind. So what will be now the measure alpha of this intersection now that I've removed something? Well, the idea is that this is going to be at least delta minus epsilon. In other words, can be made as small as I want. Okay. Is this clear what I'm saying? So alpha n of Cn prime intersection phi n1 preimage of K1. This is at least delta minus epsilon. Makes sense? Because what it is that I took out from this? I took out what is basically what was in C1 prime minus K1, but this is small. Okay, make sense? And now I iterate this construction. So I found the first compact set K1. Now I look for a second compact set K2. K2 will be a subset of X1 cross X2 compact. And with the following, and such that, let me say, and such that, you know, the measure, so alpha 2 of C2 prime minus K2 is smaller than, let me say, epsilon 2. This was epsilon 1. And then, okay. And then I repeat the construction. Okay, and etc. 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 I find the compact sets Kn inside the product of the first n guys, compact, and such that alpha n of Cn prime minus this compact set is smaller than epsilon n. So some epsilon n is just in advance. Okay. And these compact sets have the following properties. First of all, if I pick say Km and I project it onto the n coordinates, imagine that n is smaller than m. then this is included in Kn. I started with K1, with the first one. Then I build these new cylinders a little bit smaller, but now all of these cylinders have the property that when I project them on the first coordinate, I fall inside K1. Okay. So now this new set K2, I will actually build it inside this intersection. Make sense? Etc. Etc. Okay, then I have this property, and of course also I want that Kn in particular is included. In particular, is included in these sets, and in particular, the intersection of all the Kns is empty because these are included in. Should I make the intersection of these cylinders built? Sorry, phi infinity n minus 1. Okay. Because these cylinders, no, the cylinder on top of K1 was included into, into cylinder C1, etc., etc., etc. Okay. Now, and now where's the problem in here? Wait a second, I have to think 1 second. Let me think 1 second. Okay, right. So first of all, I can. Okay, first of all, I still need to work a little bit for this contradiction because I still need to tell you what is epsilon n, and basically I want this epsilon n to be sure that the sum, to pick them so small, then the sum over n of the epsilon n, say, is smaller than say delta over 2. So that even after I took away all these small sets, still the measure of the cylinders is bounded from below. Okay. So now, so basically what I've done using, so let me rephrase what I've done using this tightness principle. What I've done is I replaced the initial cylinders, which were cylinders over arbitrary Borel sets, with cylinders with base compact sets. Okay. And but still the measures are, the measures are bounded from below by some positive. This restriction thing was not I did not lose mass. Okay. And now the problem is in the fact that and now the problem is that the intersection cannot be empty, and because for compactness reasons. So and here it is, and here it is. So the claim, the intersection, the intersection is not empty. Is not. If I prove this, I'm done because I'm contradicting this. Okay. Make sense? This measure business helped me ensure. Let me be clear on this. Helped me ensure that at no step I can take the Kn to be empty. If the measure is so small and I'm allowed to throw away that small amount of measure, I'm done. So, but no. Okay. Now. This cannot be empty, and why is this the case? But thanks to this property already. Why? Let me first let's consider the following sets. let's consider the projection of all the kns on the first coordinate. Okay. For every n, this is the projection of a compact set in the product of n spaces onto the first coordinate. So this is compact. Okay, and in n this decreases. Right? But these guys are never empty because they're projection on an empty set. So there exists. So this intersection is not empty. So there exists, say, a point x1 okay. Let me iterate. Now let me consider instead of these sets. So basically the point in the intersection that I will find will have this guy as first coordinate. Let's look at the second coordinate. And what do? I pick, let me say, I don't know, k n prime. This is kn intersect. I mean, those with the first coordinate -1. Oh, excellent. No? Those guys, no, let me slice those compacts. Okay. Again, these are all non-empty, no, because of this, and they are compact. And I can iterate. Is it clear what I'm doing over here? Right? These are compact. I look at the second coordinate of this. The second coordinate of this form a decreasing sequence of compact sets, each of which is not empty, and therefore it has a second. There's a point in the intersection, etc., etc., etc. Right? So I found one point in the intersection of all of this, and this contradicts the fact that this kn were inside my initial slippers. Make sense? Please.
Then again, my intersection is empty.
Because these guys, because of this inclusion, and the fact that pi n -1, therefore of kn is included in Cn. Because of this. So Cn is the preimage. Cn is the cylinder built over some set. And I'm picking something which is included in the subset, and I'm looking at the cylinder built over it. So it's included in the original cylinder. But the intersection of all the Cn was empty. So by the really basic set here. Okay, makes sense. Did I forget anything? Let me see. No, should be okay. Right? Okay. Now I have a question. So basically, end of measure theory. I have a question, and the question is: how many of you are not familiar with the basic concepts in optimal transport, like C cyclical monotonicity, C concave functions, and this sort of stuff? So raise your hand if you are not familiar, if you've never heard about this sort of stuff. 1, 2, 3, 4, 5. Okay. So here's what I will do. I will state clearly. I mean, after the we make a small break, but after the break, I will will provide you with a list of basic definitions, and I will state the fundamental theorem of optimal transport, which characterizes optimal plans. And but I will not prove it. I will sort of describe you why that is true, but I will not prove it because that requires a couple of hours, which is an important share of the total amount of hours that I do have. In the introduction to optimal transport that I pointed you out, it's like on page 20. And so what I invite you to do is go there, read it, and if there are questions, come to me. Okay, we can also organize, if you want, an extra lecture, not on Monday and Friday. That's where we sit down and we review this basic material. The reason why I do so is that because I will not really need that much of the theory, basically. But the little bit that I need would require, just too much of investment of time. It's really not worth. Okay. And on the other hand, I would perfectly fine if, for the purpose of my course, you take as a black block this sort of basic stuff about black box. Sorry, this basic stuff about. Okay. So let's make a 5-minute break. Meanwhile, I write a few definitions on the board, and then 5 minutes, and not 10 minutes, 5 minutes. Okay? And then we continue. Hi.
First year PhD student.
So
And you said this course can be taken as a reading course, like in mass department.
to get credits. Yes, sure, sure.
Like, how would you like to evaluate this course?
Unfortunately, non-reflexive Banach spaces do exist apparently. So we have to choose which side of the story do we want to look. And for measures, we really should look at direction on previously defined objects like sets or functions. I mean, that's a kind of philosophical point of view. Right? But technically speaking, I mean, this is just a no.
Yeah.
No.
Okay. Cool.
Sure. All right. About optimal transport. So let's fix for the rest of this lecture, let's fix two Polish spaces and a map from their product to say 0 plus infinity, whatever, continues. Let me exclude plus infinity just in case. I think I can handle that. C in our mind is the cost function. So if I want to transport a point which is x on the source space to a point y in the target space, I pay C of xy. Okay. And then the optimal transport problem is as follows. Fix also. So let's say mu be a Borel probability measure on x, nu a Borel probability measure on y, and minimize. Find the integral of C xy d alpha xy among all alphas probability measures on the product with such that pi x push forward alpha is nu and pi y push forward alpha is the target measure. This is the optimal transport problem. Okay. So what does it mean? What is this alpha? Let's just clarify. So let's think for the first case. Let's say the mu and nu are deltas. So delta and x, delta and y. Okay. Then there is only one probability measure that projects. Also, pi x is the projection to the first coordinate and pi y in the second. So if both are deltas, then you see that the only chance for a measure to project on this is to be the delta in the product. So you are minimizing among a guy with one set, so that's the minimum, the maximum, whatever, and that gives you the cost cxy. Okay. More generally, if mu is delta at x, so if mu is just a delta or nu just a delta, one of the two is a delta, then there is only one alpha that does the job. So the only alpha is delta at x product nu. You can see this, think at how this shape is. So you're looking for measures on the product space. So this is x and this is y. You're looking for measures that project into x and y to the given measures. If the starting measure is an x, is a delta at x, so this measure should be concentrated on the the cylinder based in x. So there is really not any wiggling room to play. The projection onto y should be nu, and that's exercise proof that's the only measure that satisfies the constraint. Okay. Other examples. So let's see how to. So I'm trying to give you an idea of how these alphas are made. So what are these so-called the transport plans? In the general case, you have a certain measure mu here, a certain measure nu here, and these alphas are measures in the product, and you should think of it like this. The measure of a small rectangle, say E times F, alpha of such a rectangle, measures the amount of mass that mu was given to the set E that is actually going to be sent into the set F. Okay. And how much do I pay for transporting this map from E to F? Well, it's cost, no? a particularly relevant example is suppose that you have a map T from X to Y such that T push over mu is equal to nu, a transport map. Then this induces in a natural way a coupling in the following way, that alpha equal identity comma T push over mu. This is a transport map. Identity comma T is the map that takes X and returns X comma T of X in the product. And by functoriality of the pushover, if you like this sort of terminology, because the sort of chain rule, if the first margin of alpha is mu and the second margin of alpha is T pushover mu, which is nu. Okay, and this guy is made like this. So if this is the graph of T, then what you are doing is you're taking the measure mu and you're sending it on the graph of T. Right? Now, in fact, in the original formulation of the optimal transport problem, as given by Monge, one was minimizing among transport maps the integral of Cx comma T of X d mu of X. That gives you the idea that I'm sending any point X to a certain point T of X. How much do I pay in total? Well, this amount of it. Okay. This formulation, however, from the mathematical perspective, is not that good because the set of transport map per se it has no structure, could be empty, for instance, and there is no operation that you can do on maps that still gives maps, basically, and also is extremely non-symmetric. What happens if I want to transport Newton? While this, in some sense, is way better. So, for example, there is always at least one coupling. Mu cross mu, the product measure is always a competitor. So the set where you're minimizing is not that. One other thing that I want to mention is that this passage from maps T to plans is extremely common in analysis. Is what is called the study of Young measures. If you are a little bit into the weak convergence of LP spaces, and perhaps we will also encounter this sort of procedure if I will be able to when discussing regular Lagrangian flows of Sobol effect of fields. That's the first step of the is always this kind of procedure. Hey, what is this procedure that it linearizes a nonlinear program? No, in T this problem is just a mess. You have no reasonable constraint, no reasonable structure on the class of maps T, no good dependence on the cost on T and whatever. While here, in alpha, this problem is linear. And the constraint is convex, the average of alpha of two alphas is still a good alpha, right? So intuitively, in terms of, if you look back at what happens with maps, it's like saying, well, let's say that I have two maps, transport maps from mu to nu, and say, how do I take their average? Well, basically, it's like saying, well, let's send half of the mass through T and half of the mass through S. So the average of the plans induced by maps would do something like this. Okay. Now, I want to minimize something. So there is one theorem that we all know about the existence of minimizer that tells you that if you are minimizing a lower semi-continuous function over a compact set, then a minimizer exists. So that's basically almost the only theorem. Well, not really the only, but almost the only theorem we do have about the existence of minimizers. So let's try to see whether we can apply this theorem in this case. First of all, what it is so let's study the collection of admissible transport plans. So this coupling, I give it a name. Sometimes I denote sometime. I don't know if I will keep this notation later on. But so admissible transport plans. This is the subset of Borel probability measures on the product, such that this constraint is true. Okay. And the first remark is that this guy is weakly compact. In the weak topology, in the Borel space, it is compact. Okay. And why is the case? Well, because more generally, the union, let me do more generally. If, I don't know, kx and ky are weakly compact, or let me say it like this, are tight collections of probability measures on x and y with obvious choice of denotation, then the collections of alphas in the product such that pi x push over alpha fits into kx, and the second marginal goes into ky, this is tight. So tightness in some sense works well under product. So I have a tight family of measures on x, a tight family of measures on y, and I look at all the probability measures on the product whose first marginal is in the first collection, the second marginal is the second collection. This is tight. And the proof is trivial because I have to prove tightness, so I have to find this compact set on which most of these guys are this guy is almost all concentrated. So you give me epsilon, and I find k1 inside x, for which all the measures, such that mu of the complement of k1 is smaller than epsilon for every mu in this first family, right? And similarly, and I also can find a compact set inside y, such that mu of k2 complement is smaller than epsilon for every mu in ky, right? Make sense? By that. Okay, now what will be the compact set in the product space that I will pick? Well, let's look at what happens if I take k1 cross k. This is compact in the product of compact space. Right? And let me pick alpha of k1 times, of the complement of this for alpha in this set. So I'm taking the product of two sets and I'm taking the complement, right? So this is clearly, this is clearly as a set. This is included into the complement of k1 cross y, no? Union x times the complement of k2. Okay, no? It's just this guy, no, and the other guy. Make sense? So alpha of this is less or equal than alpha of this guy plus alpha of this other guy. But how much is it? Alpha of this guy. Alpha of this guy, by definition, right? This is k1. So this is pi x push forward alpha of k, the complement of k1, right? Which is smaller than epsilon, and the same over there. So tightness is right. So in particular, if I fix, if I just pick, kx and ky are made by just one probability measure, that is certainly tight, and therefore this set, I've just proved that this set is tight. Okay, so to prove that it's weakly compact is now just sufficient to prove that it is weakly closed, right? But why it is weakly closed? Well, the constraint. Well, I guess one way of seeing it is that pi x push forward alpha is equal to mu if and only if for every pi continuous and bounded on x, we have that the integral of phi x d alpha x y is equal to the integral of phi d. Right? Okay, but then you see that these are closed, weakly closed constraints. Fix phi, fix one function phi, and the collection of alphas such that this integral is equal to some given number is closed, weakly closed, right? So I'm just intersection over all the phi's and them down. Okay, so this is proof. So I have a weakly compact, and very well. Now I have compactness, so I would love my functional to be weakly lower semi-continuous, so that now the direct method of calculus operation applies. And let's look at this. So notice that the map, of course, the map that takes alpha and returns the integral, let's say, of psi xy, the alpha xy, this is weakly continuous if psi is continuous and bounded on the product, right? Now my function, my cost function is not bounded, and I don't want really to assume that, because in my mind, in my applications, they will be the distance squared over a given set. So I don't really want to make this assumption. However, the map, so what I know is that the map that takes alpha and returns the integral of the cost truncated, say at level alpha, this is weakly continuous. Because the cost function is truncated, it was continuous, no, with from 0, bounded from below. I'm cutting from above, so now this is right. But then, of course, the integral of cost, the alpha, is equal to the sup by monotone convergence, is equal to the sup over n of the integral. Right? For any alpha probability measure, this is equal to the sup. Therefore, the map that takes alpha and returns this guy is the sup of the map that takes alpha and returns these guys. But each of these is a continuous, weakly continuous map. Therefore, the sup of continuous maps is lower semi-continuous. Okay. So I have a compactness of the set, of my set where I want to minimize stuff, and the function is lower semi-continuous. Existence of the minimizer is 3. Okay? I pick a minimizer. The direct method of calculus, what's this? I want to find a minimum. I a priori don't know whether the minimum exists or not, so I pick a minimizing sequence. So I pick a sequence alpha n, such that the associated cost converges to the infinite. That, by definition of inf, exists for sure. Okay. Then I invoke compactness, in this case weak compactness, to say that I can extract a subsequence that weakly converges somewhere. This plus the lower semi-continuity of the functional ensures that the functional applied to this limit of the sequence is less or equal than the limit. But therefore is exactly equal to the minimum. Okay, so existence of the minimizer is there. There is, one of the advantages of this formulation is that existence is trivial. What about uniqueness? Of course, at this level of generality, there cannot be unique. A constant cost function, for instance, is included. And in fact, in general, I don't think we really care that much during my course about uniqueness, nor about the fact that minimizers are actually induced by a map, which is, on the other hand, a crucial aspect of the theory when you work on a smooth space, say RD, Riemannian manifold, and etc., etc. But perhaps I will touch, but in case much later on. So for the moment, what I care the most is the structure of the minimizers, and here there are a couple of remarks that I want to actually. Let me give a definition. And these kind of things work in the high generality of that I'm working right now. So let's consider a subset of the product. This guy is called C cyclically monotone. If for every choice of natural number, let's say positive, and for every choice of xi, yi in this set, y goes from 1 to n, we have that if I and also and for any choice of permutation sigma, I don't remember the notation, Sn, I guess. So the permutation of this set of n indexes, we have that the sum over I of the cost of going from xi to yi is not bigger than the sum over I of the cost of going from xi to y sigma I. Let me comment about this definition. Say that we have that our transport problem is between sort of combination of direct masses. Say that both nu and nu are 1 over n sum of direct masses over n points on the source and n points on the target space. Okay, and we have a plan, a way of transporting these masses, and we want to check whether this is optimal or not. I mean, we don't know. We pick a random one and okay, what it is that we can do? Say that we know that inside. So this plan, by nature, should be concentrated on a finite number of points, right? Okay. Say now that so let's pick n points in the support of this plan. So this point will be of the form x, y, y. So what we know by the fact that these points belong to the support of this plan is that a little bit of mass is taken from xi and sent to yi. Okay. Now let's say that we wonder whether our plan is optimal. Well, this condition must for sure be satisfied in the support, meaning, so I cannot find a finite set of points and a permutation so that if rather than sending the mass to x from xi to yi, I rather sent from xi to y sigma I cannot do something strictly better than what I was doing before in terms of total cost. You see what I mean at the intuitive level? Okay. If for some sigma I have a strict inequality, well, let me take out as much mass as I can from this sort of circle, and let's redistribute it in such a way that I get this inequality. The fact that I'm picking a permutation here is what would ensure me that after redistributing the mass, I still have the same marginal. It's not that I took out some extremely costly jump and not replacing it with anything, right? Okay, so that is a definition. A couple of other definitions are the following. A function phi from x, possibly, I guess, I never remember, so here I should pay a little bit of attention. I should be sure that should be minus infinity should be included. Okay, well, anyway, yes. Okay, a priori also plus infinity, but let me say that. So this is C concave. Actually, let me do this. Let me speak about C transformers. So a C transform, so the operation of C transforming is something that takes a real value function on x and returns the real value function of y, possibly with plus or minus infinity, and vice versa takes function from y and returns function of x. So let me start from functions on y. So let's say that psi goes from y to say r, possibly plus or minus infinity. Then psi c is a function from x with values on r, possibly plus minus infinity, and is defined as the inf over all the y's of c x y minus psi of y. It's a definition, okay? Its relation to optimal transport might be totally unclear at this point, but there is another construction that probably you've already seen that is extremely close to this one, and it is the definition of Legendre transform of converse functions. Say that, okay, if we play a little bit with signs, this inf, okay, could be a sup, and if x and y are Rd, and the cost is the scalar product, then this is the sup, no? Recall that f star x is the sup over y of x dot y minus f of y. Right. That's the definition of Legendre transform, and this is just a direct generalization of this. Don't get scared by the super inf, because this is just a choice of notation. Okay. And now, of course, a similar definition is in place if I start from function phi over x, and I use the same kind of trick to define a function of y. Okay. In general, I should pay attention that the two are not really the same thing, because C is defined on two different spaces, and therefore, in particular, can also be non-symmetric. So, doing the inf over y is not the same as doing the inf over x, but from the algebraic perspective, they are sort of the same. Okay. And now I say that the function, so a function is convex and lower semi-continuous if and only if it is the Legendre transform of something. That is one of the first theorem in convex analysis that one encounters. So it is clear that the soup of linear stuff is convex. And basically, Banach, which, okay, in finite dimension is rather easy, Banach tells you that any convex lower semi-continuous function can actually be written. And now the definition. C convexity, C concavity, and C separate differential. So phi, say from x to r, is a C concave if phi is equal to psi c for some psi. Okay, and similarly for C concave functions on y. Okay, and the C super differential of phi, this is a subset of the product, and it is the collection of couples xy such that phi of x plus phi c of y is equal to cxy. Okay, end of the definitions. Now we'll comment a little bit on this. First of all, despite the differential in the terminology, there is no derivative in here. I'm not, linearizing anything. I'm just looking at, where a certain equality goes. Also, notice that for every x and y, this inequality is always true. Why? No, because you see, right? If being an inf, no? The C transform is an inf of something, so the choice of this particular x where I'm looking is always admissible in the definition of phi c, and you get the lesser equal, right? So in some sense, you live in the C super differential if x is one of those points where the definition of the inf in phi c is actually realized. Make sense? Okay. One other thing is that if you play a little bit with these signs and whatever to reduce to this situation, then you are in the C super differential if and only if you are in the sub differential in the classical terminology of convex functions. So a point, no, you know that when y realizes the max over here, it means that y is in the super differential of in the sub differential of f. Okay. And much like in convex geometry, there is in convex analysis there is this duality between f and f star, right? Here we have the analog duality between. Actually, there is one thing that I should mention. And it is easy. And that's really the same in convex analysis. For any phi from x to r, whatever, plus minus infinity, if I do the C transform, now I get a function over y. Therefore, I can make another time the C transform and I get a function over x. And therefore, I can make another time the C transform and get a function over y. Okay, and in principle, I could go back and forth a number of times, but after I do 3 times, I go back to. Okay, check it. It's an exercise of playing with the definition. There is inf, sup, inf, and you see this works. Okay. So in particular, if phi is C concave, then phi CC is equal to phi. In fact, this is another if. No, because if phi is C concave, phi is the transform of something. So doing other two times the transform, it's like doing just once. So it's going back to phi. Okay. On the other hand, if phi is phi CC, then it is the C transform of phi C. So it is C concave. Okay. Okay. It's still, of course, totally unclear what all of this has to do with optimal transport. But here is the another easy observation. And the easy observation is this: is that for any phi, let's say phi is C concave, imply, okay, this is not really needed, but I only look at the SISSA per differential for C concave functions. Imply that phi C is a C sigma monotone. So if you believe the sigma monotonicity had something to do with optimal transport, also these conditions. And why is this the case? Well, let's look at the definition, and it's going to be trivial because so C sigma monotone means that this happens, right? So what should I pick? I should pick a finite collection of xi, yi in the SISSA per differential phi, and the permutation, right? And then I should check whether that equality holds. And so let's have a look. So I should do sum over I of C xi yi. Okay, but by definition, this means that for every I, no, let's forget about this. For every I, this is equal to phi of xi plus phi C of yi. And then I sum. The operation of addition is commutative. Therefore, this is also equal to the sum over I of phi xi plus phi at y sigma I. I just rearrange the second terms. Okay. But now again, for each term in this sum, this is always bounded from above by the cost of transporting xi into y sigma I. Okay. All right. Now here it comes the fundamental theorem of optimal transport. Makes us close this circle of idea. Fundamental. So okay, let me write fully this statement. So xy completes Polish. C from x cross y to let me say 0 plus infinity. I'm putting loads of assumptions that are totally unnecessary, but they're more than sufficient to cover the case that I actually care. Continuous. New probability measure on x, new probability measure on y. And I need to assume something. So there is, as of now, it could be that anytime I find a transport plan from nu to nu, the associated cost is plus infinity. I mean, I have no, finiteness assumption on this. And I need to, if I want to deduce something about the structure of minimizers, I really need to assume something that, exclude this sort of behavior. So let me assume that, there exists some function f in L1 mu and the function g in L1 nu such that C of x, y is less or equal than f of x plus g of y for every x and y. So, but of course, here, I mean, there's a function, not an equivalence class of function. There is a function, which is Borel and integral in mu, such that no, this is true for everything. Then the following are equivalent. And let's say alpha be an admissible plan. Okay, then the following are equivalent. First, alpha is optimal. It minimizes the cost. Okay. Second property. I should mention one thing. Okay, the support of alpha is C-cyclically monotone. I've read the statement and then I comment on it. 3, there exists phi from x to r, possibly plus minus infinity, C concave, such that the positive part of phi is in L1 mu, and so that the support of alpha is contained in the SISSA per differential of phi. All right. Okay. Let me make a few comments. First of all, I never mentioned what the support of a measure is. Perhaps let me do it now. The support of the measure is support of alpha is by definition the intersection of all the of C among all C closed and where alpha of C is equal to 1. Okay, see, for probability measures, otherwise you can adapt this to a general measure. Okay, this is equal to the complement. Okay, let me say x minus the union of all the U open such that alpha of U is equal to 0. Okay. Now, this definition you can do anytime on a general topological space. The interesting fact about separable spaces is that alpha is concentrated on itself. In general, this intersection is more than countable. So it could be that a priori, after you intersected, there are measures with empty support in crazy spaces, non-separable spaces. But this intersection you can always reduce to the case of countable intersection, and perhaps you can see more easily out of this. If your topological space is a countable basis, any union of open sets can always be reduced to a union of certain subsets of certain open sets in this base, because every open set is union of a suitable collection of sets in the basis. So that union is always at most countable. So if you have now a countable collection of open sets with 0 measure, the union is also 0 measure by countable addition. Okay, and therefore the measure is concentrated on its support. Okay. Okay, as mentioned, so I will not prove this theorem, but I will describe the proof, and then leave the technical details to you guys. Have a look to this introduction that I brought. It's not that hard. Okay, it's just long. So let me comment. So this implication actually we already know, because any time a set is so the full SISSA per differential is cyclically monotone, and clearly cyclical monotonicity is preserved if you pass to subsets by checking. So if these all, so that's there's nothing to. Okay, and let me see if there are other implications that are trivial. Okay, not really. So let me see how the proof goes. And okay, the implication 3 to 1, so proof. not really proof, but sketch of it. Yeah, the implication from 3 to 1 is the only, I mean, is the easy one. Suppose that you have phi satisfying this condition. Let me neglect the integrability issues, and let me take alpha prime and any other admissible plan, and let me try to compare the cost of alpha that satisfies this property with the cost of alpha prime. Okay, so what it is the integral of C, and this will be, I mean, it's basically the same computation that we done. So alpha is fully concentrated on the SISSA per differential of phi, right? Therefore, for any x and y that actually will matter in this integral, we do really have that this is equal to the integral of phi of x plus phi c of y d alpha xy. Okay. And now, if you believe in the linearity of integral, which is a tricky statement, of course, if plus infinity is allowed here, but under this integrability assumption, you can see that this is actually equal to the integral of phi x d alpha, plus the integral of phi y or phi c y d alpha. A little bit just check that this is true. Okay. So say if the cost is bounded, for instance, this is certainly true. Okay, otherwise you have to use a little bit of assumption. But this is equal to the integral of phi d mu, and this is integral to the integral of phi c d mu. Make sense? Right. So all these again by now you call into play alpha prime. This is equal to the integral of phi x plus phi c of y the alpha prime of xy. Right. So but this now for any x and y, this sum is less or equal than the cost of going from x to y. So this is less or equal than the integral of cxy, the alpha prime. Okay. So up to this technicality, that's the easy implication. Okay. And of course, if you believe now that this theorem is telling you something non-trivial, it means that at least one of the other two implications is not so trivial, right? And in fact, it is not the case. So let me try to illustrate why one implies two. So one implies two is done by contradiction. In fact, in some sense, okay, let me just say this. So if mu and nu are concentrated on finite sets, the conclusion is trivial. And the conclusion is trivial. Meaning that we can, I mean, that's the same argument that we've done before, right? If the alpha was not concentrated on a C-Sigma monotone set, we could rearrange the mass in such a way that to find a new alpha with strictly less cost, and therefore alpha was not on. Okay. Now all we need to do is to pass this kind of idea from the finite to the continuous case, and that's again why, and that's why the assumption of continuity of C plays a role. Basically, if so, the idea is this. So suppose that alpha, again, by contradiction, if alpha is not, the support is not C-Sigma monotone, we can find a finite number of sets in the product and the permutation where the strict inequality fails. But then by continuity, strict inequality fails on okay, the single points typically will have zero mass, right? Because measures could be diffused. But now so by continuity, we can find small neighborhoods, the product neighborhoods of these points where the strict inequality still fails with the same permutation. Okay. Now this will have positive mass, because they are points in support. And now it's just a matter of rearranging things between these points without destroying the marginal constraint and producing a new plan which still transports the mass but strictly less cost. This is basically only a technicality. Okay, but the idea is this. And 2 implies 3 is perhaps is the most I guess the most incredible thing. I mean, I couldn't believe the first time I see this. So 2 implies 3, in fact, rests upon the following very general fact: if gamma is C-cyclically monotone, then there exists, in fact, I can build, not only there exists, there is a formula producing C concave functions phi, let's say, with phi C, sorry, C subdivision phi containing them. That's totally crazy. You start with the set. The only thing that you know is that it is cyclically monotone, and you can build an actual C concave function with C subdifferential contains this. Okay, it's not obvious. In fact, in some sense, okay, a priori is not obvious. A posteriori, once you see the formula, there's really no other thing that you can do. Again, try to look at this formula in these lecture notes. But that's basically the end. This integrability condition then comes into play after the assumptions, after the assumption of the cost. Okay. Let me comment. Let me give another couple of comments about this statement. So there is one fact, among others, that is particularly non-trivial about this, and that again, a priori is a little bit surprising, and a posteriori maybe not that much. But and the fact is the following: that being optimal depends only on the support of the plan. So this means the following: pick 2 measures, mu and nu, find an optimal plan, alpha, and now pick any other measure in the product space whose support is concentrated on the support, support is included in the support of your plan. Typically, these will have different marginals, of course. But whatever their marginal are, this new plan is still optimal. Okay? Which might be strange at the beginning, but if you go back to the finite dimensional case, perhaps you see why this can be true, because I mean, in the finite direct masses, that's clear that the C-cyclical monotonicity characterizes optimality. It doesn't matter how much mass you give to each of those points. As soon as you give a positive amount of mass, you must be C-cyclically monotone, because otherwise you can permute stuff and be strictly better. Okay, so that's the same kind of principle which is at play here. And one last thing that I should mention before concluding today's lecture, and it is about the dual problem. And optimality in the dual problem, as you will see, is a direct consequence of this statement as I made it. So you have this transport problem, right? You have your mass nu, the cost, and you want to transport mu to nu in the most efficient way. I'm a transport company, and I come to you and I tell, look, I'll take care of the transport. Okay? You just pay me phi x for any time I pick a unit amount of mass from the point x. And you also pay me psi of y anytime I drop a unit of mass at the point y. Okay? How much is the reason? So first of all, what it is a reasonable set of prices that I should put if I want to be sure that I could be in some sense a good match for you? Well, certainly in general I would like phi of x plus psi of y. This should be bounded from above by cxy. Otherwise, my prices are too high and they're not convenient for you. Okay. And of course, the total cost that I heard, the total, the total price that I get once I fix this, if you allow me to do the transportation cost, is the integral of phi d mu plus the integral of psi d mu. That's my total revenue. Okay. And it is obvious that my total revenue is for sure less or equal than what you pay for the cost if you come with me, because this, if alpha is an admissible plan, then this is equal to integral phi x plus psi y the alpha xy. Okay, and by this condition, this is less or equal than the integral of the cost the alpha, right? Okay, And so my problem, you have the problem of transporting. My problem is to maximize this subject to this constraint. So that's the dual problem of transport. And what this inequality is telling is that the sup of the dual is always less or equal than the inf of the primal problem. Okay. And a corollary of that statement is that equality can be achieved. There exists phi and psi, which actually I can take as the C transform of phi, and phi is C concave actually also. So that equality holds here. I mean, so that equality holds. So the sup of the dual, so the max, this becomes a max of dual problem for dual problem. Equals the mean of the original problem. Just pick phi, this phi. Okay. If I have phi and phi C, the C transform certainly satisfies this constraint. In fact, for any phi, if I pick as psi the C transform, I get this constraint by definition. But then I have an optimal, I have an optimal plan alpha for which equality holds in, right? Okay. So just a couple of conceptual remarks. Anytime you are minimizing a linear function over a convex set, this is what sometimes is called well, I mean, it's a linear optimization problem, and these kind of problems always have in finite dimension a dual problem, where you minimize or maximizing another function over another convex set. And one feature that occurs in this duality is the relation between the constraint and the cost function. Notice that in the cost problem, so of course the data of the problem in both cases are the starting measure, the final measure, and the cost. These are the data. Now in the original, the optimal transport problem, the unknown is the alpha. And so the constraint is alpha being admissible, right? So the constraint calls into place the measure, and the functional to minimize is this that calls into play the cost. In the dual problem, things happen in the other way around. So the constraint takes into account only the cost, and the functional to maximize takes into account only the measure. Okay, this is a common feature on this duality program. And what it is, perhaps the one other thing that I want to mention is that and then I will conclude. By the way things are written over here, it might seem that you start from an optimal plan and you get a C concave function such that this is true. Okay. What is actually, in fact, worth to mention is that the same phi works with any optimal plan, and vice versa. That basically any optimal plan works with any phi which maximizes the dual problem. Let me point out. Let me clarify what I mean by this. Actually, let's have a look to this. So as soon as phi, psi, and alpha are admissible, I do have this inequality. I'm almost done. 30 seconds and I'm done. We do have this inequality. Now, if alpha is optimal, and psi also with psi are optimal and dual problem, then we have equality over here. Right? Now take another beta, which is optimal for the cost. Then we do also have that the integral of phi to psi in the beta is equal to the integral of the cost function in the beta. Right? Because it is equal to the cost function in the alpha, and the minimizer is the same. But this is always less or equal than cxy. So if I have the integral of this function in the beta is equal to the integral of this function in the beta, it means that I'm concentrated on points where phi x plus psi y is equal to 0. Make sense? Think about this. I'm saying a triviality. I'm saying that if I have another plan which is optimal, the cost of this other plan is the same as the cost of ours. Right? But on the other hand, the integral of the cost should be, in principle, should be greater or equal than the integral of phi x plus psi y, because of this inequality. But if the integrals are the same, it means that I'm concentrated on points where equality holds. Right? Okay. For today, that's all. We resume on Friday at same hour, 10:30. Okay. Unless there are questions or. Okay. If not, goodbye to the person following online.
Thank you very much. Very interesting mathematical arguments.
Thank you. Thank you.
Appreciate the details.
I cannot hear.
Was there a question? I couldn't hear the last sentence.
No, I said I appreciate the mathematical.
Okay. My pleasure.
Very elegant argument.
My pleasure. See you on Friday.
You're a good teacher.
You mentioned something about